if we have no grain boundaries, then what are the things which are going to be different? So first of all, you will not have pileups at the grain boundary. Grain boundary, which is a huge source of dislocation. So grain boundary as a source of dislocation will be gone. So that part is not there. So if we are talking about single crystal, then we will not be, the rate of production of dislocation will decrease because we don't have grain boundaries anymore, right? So these are going to be some differences when we talk about single crystal. Apart from that, if you consider FCC crystal, so in FCC we know that the slip plane is this one. Okay, so now there will not be other slip systems which will be in a different orientation. So all this plane 111 plane will always be either in this direction or parallel to that, but there will be family of 111 planes. So there can be one bar 1, there can be 1 bar 1 1, and so on. So FCC is the only system in comparison to BCC and HCP where the differences because of many things do not show that much effect, because FCC crystal has very efficient 12 slip systems in it, and we will discuss more on this. And this is one of the reasons why FCC crystal is more ductile in comparison to BCC, for instance aluminum in comparison to iron, which is BCC. And if you compare zinc, which is HCP, or magnesium, which is also HCP, you will see that these HCP crystals are more brittle in comparison to FCC and BCC because they don't have much slip systems. So we will talk about strain hardening, and we know that strain hardening in the plastic part of the curve, which is described by this equation which we have discussed before. So this coefficient or exponent which describes the strain dependence of stress, that exponent is called strain hardening exponent, strain or work hardening exponent. Okay, because if you need more stress to create the same amount of strain, right, so then you can describe strain is equal to sigma by k to the power 1 by n, right? And if for the same amount of strain in the next increment of strain, if you need more stress, for the same amount of strain, if you need more stress, this power has to be decreasing. That means n has to increase, right? So n, or if you plot log of sigma is equal to log of k plus n log of epsilon, then the non-linear part of our stress strain, so initially it is linear, then it becomes non-linear, right? So the linear part is described by Hooke's law, which is sigma is equal to elastic modulus into epsilon, and then the rest of the part is described by this equation, right, into epsilon to the power n. And if you plot this non-linear in log plot, then it will become a straight line, and the slope of that straight line, which will describe the rate of change of logarithm of stress versus logarithm of strain, will be the hardening exponent, and that will be this n parameter. Okay, so all this information we already have. So now the mechanism by which the strain hardening occurs. So we know that when we apply stress, the material deforms and proportionally the strain appears in the material, and so it follows a linear law to a certain extent, and that point where it changes from linear to non-linear is called the proportionality limit. Okay, and many a times that is also the yield strength, beyond which you have a non-linear behavior or correlation between stress and strain. Okay, so if it would have been like this, then we don't need any stress increment to deform from this place to this place. Okay, so there was no hardening, and this case where at the same amount of stress the strain increases to infinite levels is called ideal plasticity, and the material will be called ideal plastic. Okay, the other form could be that in order to increase the strain, you don't really have to increase the stress, but the stress will drop, and this will be called strain softening, right? And if you have to increase the stress in order to deform from one strain value to another strain value, so that is called strain hardening. Okay, so we have a situation where there is hardening, we have a situation where there is softening, we have a situation where there is no hardening or softening, which is ideal plastic case, right? So these three kind of behaviors we can have. We have studied about strain hardening type of stress strain curve, which was our type 2 curve, elastic homogeneous plastic. We also studied about the strain softening kind of behavior, which we studied in type 5 curve for polymers. Okay, but now we are talking about strain hardening in single crystals. So the first explanation based on dislocations was given in the terms of barriers to the dislocations. So the proposed theory was that dislocation, they pile up at the barriers. Okay, so let's imagine that there is a precipitate. Okay, and this precipitate has to be incoherent in order to stop a dislocation. Okay, it has to be incoherent. So precipitates can be of different types. Precipitate, once they start precipitating, so for example you have aluminum copper system. Okay, and maybe you have studied this part where precipitation happens in aluminum copper system. So what happens is that copper starts depositing on one of the plane which will be common between the crystal of aluminum and copper. Okay, so then copper will start depositing there, and then it will slowly, so more and more copper will deposit there, and that will be kind of uphill diffusion against the Fick's law, where atoms diffuse towards the direction where concentration of that atom is already high. Okay, so now copper will be depositing there, then copper will start making its own crystal, but that will not happen in one stage. It will take a lot of stages to reach there. So initially when you have a very small colony of copper in aluminum matrix, so let's say this is my aluminum matrix, and I have the unit cells, which I can describe like this, right? So all these boxes, you can imagine those to be unit cells in 2 dimension. Okay, now what happens is that a small colony of copper forms somewhere inside, and obviously because copper is a different atom and it's not aluminum atom, it has a different size. So if the size is different, if the atomic size is different, the lattice parameter will also be different. Okay, so now what has happened is here there is a region where lattice parameter is different from the matrix, and this part has one-on-one correlation with the matrix, right? So not a single layer of atom is missing if you follow this path. Okay, or if you follow any path, if you follow this path, you will always have a path, even if you go to this zone which is copper zone and this zone which is aluminum zone. So this is one-on-one matching. So if you have a dislocation, okay, and how will you have a dislocation? You can have a dislocation which will be an extra half plane, right? So let us say that on this direction I have an extra half plane which is moving. Okay, so it moves there, then it moves there, and so on, and then it goes, and when it reaches this interface, right, it may have some strain because the atomic size has changed, but this dislocation, which is not related to atomic size, dislocation is just line, just the boundary between that extra half plane and missing plane. So that boundary can still move in this zone and also come out of it. So this is one-on-one matching. So this is a coherent precipitate. There is complete coherency. Okay, then what happens? Slowly they try to change. Okay, so the copper now tries to have its own identity. So in that case, what will happen is that you will not have one-to-one correlation. So you may have this matching, but you may not. So this layer might be missing, and then this layer may have, and so on. So this may be there inside, but the next one is missing, and then the next one is there, and then the next one is missing. Okay, so something like that can happen. So now if you have a dislocation here, this can move inside because there is matching even from outside the matrix and inside the precipitate. But if you have a dislocation here, then that will just pile up here, right? And then other dislocation which is on the same layer will come again and get blocked here, and so on. Same thing will be happening to all the dislocations which are coming there. So this is called pile up of dislocation, and this kind of precipitate is semi coherent precipitate, right? And then you will have the final stage where you will have no matching at all. So in this case you actually have, so how this precipitate is there, it forms by creating dislocations at non-matching surface. You know what I mean? So this layer is there, but so let me name these things. So this one, the first layer, which has a matching inside the precipitate, that is one. Then you have second layer which has no matching inside, then third layer which has matching inside. Okay, now the first one has matching inside the precipitate, so there is no problem. Second one is a layer of atom, right, and that layer of atom is missing inside. So what is that? It's a dislocation at the boundary which has this kind of symbol. So atomic layer is there and that is missing inside the precipitate. So you have to put a dislocation there, and then it's okay, right? Again, if you have, so So you see that this has a matching inside, and then the second line has no matching inside. So this second layer, this line is actually a layer of atoms, and that layer of atom is missing inside. So what is that? That is again another edge dislocation, right? So in semi-coherent interface you will have a lot of dislocations there. And then in the final form of precipitate we'll have copper having completely different lattice with no matching at all whatsoever with the matrix of aluminum. Okay, so this will be incoherent precipitate. Incoherent precipitate. So this incoherent precipitate will block all the dislocations from all the direction, and they will just pile up at the interface. Okay, so in a single crystal you don't have grain boundary, but you can have precipitates which can act as a barrier. Okay, so now we know about one barrier which can exist in a single crystal. Let's talk about other types of barrier which can exist in single crystal on next page. So there can be precipitate which are barriers. Then the dislocations are barrier for themselves also. Okay, so they are barriers to themselves, but before that, before we go to the dislocations acting as a barrier for them, their own movement, the theory which was given to describe strain hardening said that dislocations, they pile up at the barrier. Okay, and so this is an edge dislocation. Let us assume that this is an edge dislocation in FCC, so I will have A0 by 2 110 kind of dislocation which is moving in 110 direction, right? And they keep on piling up at this interface because there is a precipitate. That means 110 direction does not exist after this point. Okay, so this dislocation now cannot move, and I am applying a shear stress and asking them to move. So dislocation number 1 moved, reached this boundary, now it cannot move, so stayed there. Dislocation number 2 moved and it cannot go any further because there is a repulsion in dislocations of the same sign, and you see these two dislocations are exactly the same, so two half planes cannot be together because that will create more strain in the lattice. Okay, so there will be some repulsion, there has to be some complete planes between these two, so it will not go neck to neck with each other, right? So this has also stuck here. Then number 3 dislocation also stuck, 4 also stuck. Now I will have to do something so that this barrier either is crossed or broken, so that the dislocation can pass through, move on, or do something, so that slipping is allowed. If that does not happen, then there will be no strain, no slipping, so stress will cause no strain. I will have to increase the stress. Okay, and then when I increase the stress, it can either cut this precipitate through, or it can cross slip if possible, so it can find another plane which is parallel to this, but the precipitate is not there, and so this is another 110 plane direction, 111 plane, a parallel 111 plane. So all these dislocations, so first dislocation has to cross slip, come here, then move. It may then come back to that plane if it wants, but not necessary. It can also move on this plane. Okay, so cross slip will happen when you have stacking fault energy high in the material. So in FCC, cross slip can happen very easily. But in BCC that is not possible, so you will have to break this precipitate. Okay, once this precipitate has broken, then the other layer is ready for this dislocation and it can pass through that. Okay, so that will be shearing of dislocation, sorry, shearing of the precipitate. If it is a coherent precipitate, then it can pass through. If it is a semi-coherent in precipitate, then it can be blocked also. Okay, so this was one of the theory which proposed that because dislocation pile up and you need more stress for them to either break the barrier or pass through by some other means, so that's why you need more stress to deform, and that explains strain hardening. That was one of the mechanisms. So for this the theory said that they pile up at the barriers. One barrier could be precipitates, there can be foreign atoms, so like solute atoms, so we can have substitutional atoms or interstitials. Okay, so these can also block the dislocation, pin the dislocation, and that part we have already discussed before, right? Other kind of barrier can be Lomer-Cottrell kind of barrier, which forms by dislocation movement. So Lomer-Cottrell barrier, we have discussed that when two 111 plane intersect with each other, so I have 111 plane here and I have another 111 plane there, and I have a dislocation coming along this direction and another dislocation coming along that direction, and they will block at this intersection point. And the real mechanism, so this mechanism was proposed by Lomer, and this kind of reaction what Lomer proposed, that two perfect edge dislocation, they join each other and create a dislocation which cannot move, which is sessile, that was never found in reality. So Cottrell modified this and said that the perfect dislocation before coming to the interaction of these two 111 planes, they actually dissociate into partials, and those partials get blocked here. Okay, and that's how it got the name of Lomer-Cottrell's barrier. And this does not require any change in orientation. This can happen in FCC single crystal because you have more than one 111 plane in one unit cell itself, right? And those are not parallel. So it is possible in FCC single crystal for 111 planes to intersect with each other. So this kind of intersection is possible in FCC single crystal, so this can also be one type of barrier in the single crystal. Okay, so all these types of barrier can cause the dislocations to be blocked, and you will need more stress to break these barriers, and therefore strain hardening can be explained, right? So now come back to this diagram. So I have a barrier, and this barrier is a representation of any kind of barrier. It's a general barrier, and dislocations are coming and piling up there. Okay, so let me make a bigger boundary. So dislocations are coming and piling up. Okay, so this pile up will be true not only for edge but also screw dislocation, but I'm drawing only edge dislocation. Okay, so but it will be true for screw dislocation as well. So this is a barrier boundary where all these dislocations are getting blocked. Okay, and I'm applying my stress so that the shear stress is in this direction. Okay, now what will happen if I reverse my direction? So I'm applying a stress of tau, right, and then I deform to a certain strain of epsilon 1, and beyond this I cannot deform if I don't increase the stress, because all these dislocations are blocked, right? Now what if I change the direction of my stress? What if I reverse it? So I apply minus tau. What will happen? First of all, if I created any dislocations from the sources because of stress, I will not have to create those many dislocations when I apply the stress in the reverse direction, because I already have these dislocations there, right? What I'm trying to say is, because of stress, dislocations can also be created. The sources of dislocations can get activated, okay? And this phenomena can happen even in polycrystalline material, but for this point of time, don't think about that. So if my in an annealed material, you can have 10 to the power 5 to 10 to the power 6 dislocations per centimeter square. Okay, so these many number of dislocations per square centimeter you can have in annealed metal. Okay, so but if when you start deforming, so in a cold worked steel you can have double of it, so you can have 10 to the power 11 to 10 to the power 12 per centimeter square number of dislocations. So by doing cold working is deforming the material at room temperature, so by doing that you increase the number of dislocations almost double of what it had at the annealed condition. So deforming a material can also activate the sources of dislocation. So if you had less number of dislocations, you might have increased those dislocations. All those dislocations got piled up at this barrier. Now if you do the reverse loading, then you don't have to create those many number of dislocations. That is one factor. And second one is, these dislocations which were blocked, they are not blocked in this direction. Okay, so they can slip or glide in that direction very smoothly. Okay, so what will happen if I'm deforming? This is my strain axis and this is my stress axis, and I go elastically deform, follow Hooke's law, then I have yielding and strain hardening. Okay, the dislocations are getting piled up, I'm breaking it to a certain extent, then I stop. Now I unload it. Okay, I unload it, so there will be this much amount of elastic recovery. Okay, so then I reach this point, and then it will not go beyond, because that much is my plastic strain, right? Now I apply stress in the reverse direction. So this is my yield strength, right? This is my sigma naught yield strength, and this, let's say, is tension. Okay, so this is my sample, and when I fix this part and apply stress in that direction, that is tension. Okay, so this is that quadrant of tension. Okay, then I reverse my direction. So instead of applying stress in this direction, now I am applying stress in this direction, so I am compressing. Okay, so this is my compression quadrant. So what will happen? I go there, and then I again have this plastic deformation, right? So the difference will be that if you went if it took this much amount of stress to plastically deform, meaning that my yield stress in tension direction was sigma naught, and if my yield stress in compression direction is this, sigma C naught. Let's call that sigma T naught. So sigma T naught will be greater than sigma C naught, meaning that yielding will start earlier in the reverse direction because I have easier movement of dislocation if I reverse my direction of stress. Okay, this is well explained for single crystal because it's similar, but when you have polycrystalline material, things will be cancelling each other out because of the random orientation effect, right? So but even then you see this kind of effect in polycrystalline material also, and this effect has a special name. It is called Boschinger effect. Boschinger effect, or the analysis of back stress, which should be lower if you reverse the direction of stress, usually can be seen experimentally in zinc crystals. And the reason is zinc is HCP, so you don't have many slip systems, unlike FCC where you have 12 slip system, and all those 12 slip systems are very good, very efficient. So in HCP, the slipping in zinc only happens on the basal planes. Okay, so you don't have much intersection of the planes, so you only have pile up, and that you can analyze very easily in the zinc crystals, and you can see Boschinger effect in the zinc. But in FCC, you will not see this Boschinger effect in all the FCC material, because FCC is so ductile that this effect does not matter. So in many metals, Boschinger effect is not very prominent. You may not see it. Okay. But the concept of back stress in single crystal explains the strain hardening, and we will see that how that is the most prominent or most effective reason of strain hardening in single crystal, and whatever happens in single crystal also happens in polycrystal, apart from other things which can happen in polycrystal, for instance grain boundary interference with the things. Okay, so let me go to the next page. So the pileup on barriers apart from those which are created by dislocation, for example Lomer-Cottrell barrier, happens at a longer distances. Okay, so any barrier, for example precipitate, that can block the dislocation at a very long distance, and therefore these type of barriers are relatively temperature independent. And we will see why. We will see why the opposite is true. So why short range blocking of dislocations are not dependent on are dependent on temperature comparatively. So this is true for longer distances barriers like precipitates. Okay, and now we will discuss how dislocations can block each other. We discussed about Lomer-Cottrell, but dislocations can intersect with each other and block each other also. So when two dislocations intersect with each other, they can create two types of entities. One is called a jog and another is called kink. Okay, so a jog is a part of a dislocation which is out of the slip plane. Okay, out of slip plane, and kink is a part of dislocation which remains on the slip plane. So let us now consider an interaction of an edge dislocation and a screw dislocation. Okay, so let us see what happens. So imagine that this is my edge dislocation. So I have an extra half plane like that, and this thing is moving in this direction. Okay, so that's my Berger's vector, and the dislocation is moving. Okay, so let me have an extension of the plane on which this edge dislocation will be moving. Okay, now if you remember our diagram where we described the stress on the screw dislocation, so let us say that the screw dislocation is making this type of step. Okay, and so it looks something like that. Okay, right, and this extra half plane is moving in this direction, and then this part of the atoms, they are moving, and the other surface is having a dip, so they're just, the surface is going down by 1 unit atomic distance. Okay, so what will happen after these two intersect with each other will be that, so this edge dislocation which was moving now will have, so let me make this a little longer. Okay, so that was moving, and then so that part of edge dislocation will remain like that, and this edge dislocation will have this 1 atomic distance drop because this screw dislocation just passed through edge dislocation, and the rest will remain like that. Okay, so what happened? This part of edge dislocation is out of the slip system, out of the slip plane. So this is a jog. This is a jog. Okay, this part, so if this is my slip plane, this is my slip plane, this is perpendicular to slip plane, so that part cannot move. Okay, but it can move if these two parts of dislocations are moving. So if one part is not moving and another wants to move, that movement is not possible. Okay, so if the other part or this part or that part, any of these two parts are blocked, then the whole thing cannot move, but it can move as long as both parts are moving. Okay, so this is a jog. Now what, something will happen to the screw dislocation also. Screw dislocation, and now I will, instead of drawing that cylinder, I will just draw the screw like a line. That screw dislocation will have a shift because of edge dislocation part, edge dislocation's direction. Okay, so that will just have a shift along the direction of the Berger vector of the edge dislocation. Okay, so this part of screw dislocation, this part, so let's call this A, B, B dash, C. So A, B will be moving, can move along their Berger vector, B dash C part can move along their Berger's vector, but this part has a Berger vector because it's a part of the screw dislocation, the screw dislocation AC, which was like this. So AC. So this part BB dash is a part of screw dislocation which has a Berger vector perpendicular to it. So this is like an edge dislocation part of screw dislocation. So edge part formed on a screw dislocation. Okay, the whole thing remains on the plane. Okay, so this is a kink. But this kink, if any kink forms for an edge dislocation, that is no problem, that can move because everything on the same plane. But for a screw dislocation, if a kink forms with an edge kind of orientation, right, so part of dislocation which has a Berger vector perpendicular to it, that part is kind of an edge dislocation, but that part is in a screw dislocation, so that part cannot move, it's not possible. Okay, so jogs, so this kind of intersection, they usually don't stop edge dislocation, but they do stop screw dislocations. This kind of interaction stops screw dislocation, different other types of interaction. So you can have edge and edge interaction, you can have edge and a screw interaction, and you can have a screw and a screw interaction. So when two screw dislocations will be interacting with each other or intersecting with each other, you will have this kind of formation in both of the screw dislocations. Okay, and there is something important about a screw dislocation as well. So you know that edge dislocation requires a plane for movement. Screw dislocation does not need a plane. Okay, so screw dislocation can move in almost any direction. It can move to any plane as long as that is a slip direction in the system. So in FCC, for instance, the better example will be BCC. So in BCC, you have the slip direction in BCC is slip direction in BCC is 111. But the planes, there are many planes on which slip can occur. Okay, so what do you get from this information? In BCC, you have this direction of slip. This is my slip direction. Okay, but you have planes which are like 110 or 112 and other planes, many planes. So what do you get from this one? The information is that in BCC you can have many more screw dislocations in comparison to edge dislocation, because screw dislocations, as long as they can move, they don't need a plane for movement, so they can move from one plane to another plane as long as they are moving in 111 direction. Okay, so they are plane independent. So screw dislocation really make it very easier for deformation to occur very easily. And if you did not have screw dislocation in the material, the strain hardening would have been very high. So if somehow you can take the screw dislocation out of the system, then instead of having strain hardening like this, you will have strain hardening like that. Okay, because screw dislocation really make the material deform very easily. Okay, and this kind of intersection, when they block screw dislocation, that hardening is much more, but then that hardening is short range, so at a shorter distance. Okay, and these are temperature dependent. So if you increase the temperature, what will happen? If you increase the temperature, this thing can move. Okay, so a screw dislocation, when a screw dislocation moves in the Berger's direction, or an edge dislocation which moves along its Berger vector, these kind of dislocation movements, which are also known as glide or slip, are conservative. Okay, nothing happens in this case. A half plane is moving, so nothing is created, nothing is destroyed. It's a conservative movement. But when you have a non-conservative movement, which is climb, in which case locally you have vacancy creation and interstitial creation. And globally you do have conservation, but locally these are non-conservative movement of dislocation. So when you increase temperature, non-conservative movement of dislocation is possible. Also, if you increase the temperature, cross slip is possible. Cross slip becomes more easier. So these barriers of dislocations, which are created by their own intersection with each other, can be crossed by increasing the temperature, and this is why the strain hardening exponent changes if you change the temperature. So if this is my temperature T1, this is my temperature T2, this is my temperature T3, then T3 is actually a lower temperature. So T1 is a higher temperature. So as you go higher, you will have more and more softening in the material. The strain hardening component will decrease as temperature increases, because dislocation barriers can be crossed easily. Cross slip can happen, and the parts which are sessile can move by non-conservative movement, because vacancies can come in the system and they can enhance climbing of the material, of the dislocations. Okay, so that can happen. That is the effect of temperature, and that is the effect of short range barriers and longer distance barriers. So now let's go to the next page. So if you plot now the stress strain behavior, so single crystal does not mean one unit cell. Single crystal means we have only one orientation in the specimen. Okay, so in the single crystal, if you plot so you will have shear stress versus shear strain if you are plotting the single crystal stress strain curve. Okay, because if you apply normal stress, then that normal stress will not cause any deformation because it's a single crystal. In a polycrystal, when you apply a normal stress for many grains, those act as a shear stress. Okay, so there you can have deformation, but if you are trying to deform a single crystal, you will have to apply a shear stress. Okay, and the response will be a shear strain. So my shear stress and shear strain response looks something like this, till where you have a very small increase in the strain hardening exponent. Okay, so very small strain hardening and kind of constant rate of strain hardening. So that is my stage 1. Then I have another stage where the strain hardening exponent is kind of linear. Okay, so that is my stage 2, and then I have third one where again the strain hardening has decreased a little bit, and that is my stage 3. Okay, so this kind of behavior for a single crystal was explained by Seagar. And so what happens in stage 1? Why the strain hardening is very small? This stage 1 is called the region of easy. Okay, so here the dislocations, they move very easily. They don't have many barriers. Okay, and the usual barriers. So now what is happening here is that you need some amount of stress, which is the critical resolved shear stress for slipping to start, for dislocation to start moving, and we will talk about this resolved shear stress later on. So you need some amount of stress before the slipping starts, before the dislocation starts moving. Once they start moving, they are not going to intersect in the initial part with each other. depending upon what is the number of dislocations you have in the system. If you have already a very high number of dislocation in the system, they are going to interact with each other. But if you have low amount of number of dislocations in the system in the initial part, they are not going to interact with each other. They are going to flow, okay, and they're going to only stop at the barriers like precipitate or something, and which is a longer distance barrier, okay. So it's a region of easy glide, because short range barriers are not so. In a short range, in every step, nothing is stopping dislocation. Dislocations are moving for a longer distance, and some of them are stopping, but not all of them are getting stopped, okay. So this is a place where the movement of dislocations is mostly uninterrupted, and mostly the movement of dislocation occurs on one single slip system. And this is why stage 1 is also called laminar flow. And I have told you a few times before that movement of dislocation or phenomena of slip can also be visualized as a laminar flow, as a layer of less viscous liquid flowing over a more viscous liquid, okay. It will not look like that because in solids you have polycrystalline material. So solids usually are, metallic materials are polycrystalline, so you will not have movement only in one direction, you will have movement in all the directions. So that cannot be called a laminar flow, that will be a kind of a turbulence. But turbulence cannot exist in solids because solids are ordered structure, and that too when they are crystalline. Only then we are talking about dislocations. So that's why we don't compare it with liquid. But when you have slips happening only on one system, then it will look like, and it is like, a laminar flow of material. And that's why it is called laminar flow, stage 1. In stage 2, what happens is that now dislocations which are moving very easily in stage 1 will now interact with each other. So here you had longer distance barriers, right? But now here what will happen is that dislocations will start intersecting each other, okay. And once they start intersecting each other, they will be creating blockage, like Lomer-Cottrell barrier, like jogs which cannot move, and that's how the dislocation will be blocked, and you will need more stress to break them, to make them flow, and therefore strain hardening will occur. This is a shorter distance phenomena, okay, because as soon as a dislocation is moving, at a very next stage you have another dislocation moving which intersects with each other, blocks it, and if you break it, they again move but again get blocked, okay. So this is comparatively a shorter distance phenomena in comparison to meeting with a precipitate or something, which depends on what is the number of precipitates you have, okay. So this is a long range, longer distance phenomena. So here dislocations will be getting blocked more and more, but also will be unlocked if you increase the stress. And this phenomena is, so you can have Lomer-Cottrell barrier and other kind of barriers which can stop dislocation. In this stage 2 you will have more than one slip system active, and that's why you will have interaction of dislocation. Otherwise, if you have only one plane, okay, along one zero direction, then it is less likely that two 111 planes will be intersecting with each other and they will be blocking each other. So that is highly unlikely if you have only one slip system. So obviously you have more than one slip system, it's not a laminar flow, you will have dislocation, intersection, and you will have barriers. Okay, so stage 2 usually is, if you take the strain hardening coefficient divided by shear modulus, so trying to normalize this variable, it's independent of stress, temperature, so not dependent or not a function of stress, temperature, or orientation, or purity. So purity is like if you have a very, so if you decrease the defects in the material, the strength increases. Okay, so if you are making pure and purer material, you can actually achieve the theoretical cohesive strength of the material. But this part, this is stage 2 part, where dislocations start intersecting with each other and all those things happen, this part will remain the same. So the slope here, the value of n, will not change even if you attain 90% purity or 80% purity or 70% purity. And purity in the sense of not chemical composition, but in the sense of defects in the system. Okay, so that does not play a very important role here. What happened in stage 2 can be described by that the shear stress is a function of a constant of proportionality and shear modulus, Berger vector, and dislocation density. So in stage 2, dislocation density matters. If you have more number of dislocations, then they will be intersecting more, blocking more strain hardening. Okay, so this rho defines the dislocation density. Okay, and this tau naught is the stress, shear stress. It's a shear stress to move a dislocation in presence of another. You know that one dislocation applies a force on another dislocation. Okay, so a dislocation will have a force, and that's why you have repulsion and attraction. Okay, so a dislocation applies a force on another dislocation, and this force is minimum when they are at 45 degrees to each other or 90 degree to each. So either in that direction or down, when they are arranged in this way, they have minimum forces between each other, and this has an effect which we will study later on when we talk about recovery and recrystallization at some point of time. But in stage 2 of single crystal deformation, where the strain hardening exponent is linear and it's a constant, it does not depend on the stress or temperature or orientation or purity, there the phenomena can be described by this equation. Okay, and G is shear modulus, B is Berger's vector, alpha is a constant, and so on. In stage 3, you see the rate again decreases, but it is increasing, but the strain hardening exponent is lowest in the third stage. And what happens here is that it is called dynamic recovery. Dynamic recovery, meaning that whatever was happening so far to harden the material is somehow getting countered by some mechanism. So something is creating or generating softening in the material also. So the overall will be moving easily. So what these phenomena are? Cross slip. If cross slip happens, then a blocked dislocation can go up on a parallel plane and move easily, right?